Good evening, students. Good evening, everyone. Tamanna, Radhika, Jyotsna, Aman, Raghavan, Maltesh. Welcome to today's evening class. So today we will be discussing about transmission of heat. This is one of the important topic in JEE NEET perspective. At the same time, there is a very safer part in this chapter that we don't have much of a concept to learn here, more of problems. One or two concepts. You will see majority of the overlapping things with current electricity and hydrodynamics at the same time. So there are wherever you see the current, whatever the type of current that you see, you can use these questions and the same formulas will be quite relevant at the same time. So let's try to see. So today's heat transfer chapter. Before that, let's take up the question from the previous CPP where majority of the students have done a mistake. That might be a little confusing. I will try to give you an understanding of this one. See, the question was, if the specific heat of a substance is 0, it means the options were body gives out heat easily, body takes in heat easily, the third one, body does not receive heat at all, none of these. These are the things. Now let's try to have a conceptual understanding here. Here the specific heat of a substance is 0. Let's take few examples. We say water has got highest specific heat, correct? Specific heat compared to the liquids. So there is the reason why it is being used in what we say coolants. What does it mean? It means that highest, this is highest. This means that this will rarely accept heat or slowly accept heat and slowly gives out heat at the same time. So highest specific heat means that the reception at the same time the giving out both will be slow. So as you move on higher the specific heat, this giving out becomes rare and rare, or it is slow and slow and slow, so that the higher specific heat of a body having higher specific heat tries to hold back the heat for greater time or doesn't accept the heat easily. Now here if you come down, so that means to say with that analogy, the lower specific heat or a specific heat of a substance which has got lower value compared to water should give out heat little easily. Say for example silica for that matter. So silica, what happens is that this gives out heat easily and accepts heat easily because of lower heat capacity. That is the reason why sand they get heated up very faster in the day and gets cooled also at night faster. This is the reason. So according to this analogy, the body with specific, so lower the values, the acceptance or giving out heat becomes more easier or faster. According to that, the answer A is more appropriate. And I keep telling to the students in competitive examinations, try to check, not every time you are asked to take the correct answer while you are asked to take the appropriate answer. So there is a very slight, subtle difference between these two. Appropriate. There may be two answers which may look alike, but one is more appropriate compared to other. So you need to be very, very careful when you are reading the question and understanding the option also. The comprehension skill of a student matters a lot. So now, hoping that this could, why not see? Arpan is asking, body doesn't receive heat at all. It receives. He is not saying that it is not receiving at all. It is not stopping. Understood, Arpan? I hope you are following this one. It is not stopping that, but it receives and gives out faster. Body stopping heat, we call it as bad conductor. We are not saying that it doesn't have a specific heat capacity or something like that. I hope you understood the difference between these two. I hope, Shailendra. Yeah, Arpan, I said the same thing. Body does not receive high heat at all. It receives heat, but gives out faster. That's what I mean to say. So now, today's goals for the class, we will take up transmission of heat, different modes of transmission, conduction of heat, steady state, law of thermal conductivity, and growth of ice on lakes. These are some of the important topics or important concepts from the competitive examination point of view. So we will take up one by one. So introduction, the transmission of heat. You know, the transmission of heat, we have understood how, what about heat and specific heat capacity and all these things. And today, now we will try to see what is the transmission of heat. The transmission of heat happens in three different ways. We say that as conduction, convection, and radiation. So these are the three ways the heat is going to get transferred. Today we will be discussing conduction majorly, a little bit of a convection. Radiation we will take it up in the probably in the subsequent chapters. Now we will start with the conduction. So what is the meaning of this conduction, how it happens, and all these things. Let's try to understand this. Conduction of heat, it happens in the presence of media. We need some medium for the body to conduct the heat. So what exactly happens here is that the heat, as the temperature of a body is increased, let's assume, let's say we will take two bodies. This is at a temperature, let's say T1, and let's have another body which is at a temperature T2. Now, getting at the microscopic level, the temperature, let's assume that here T1 is, let's say, greater than T2, or T2 is greater than T1 for any of our understanding. Let's say T1 is greater than T2. So here we know that the average kinetic energy per molecule, or the average kinetic energy of the atoms, here it will be greater in one compared to kinetic energy in the case of the second one. Now let's bring these two in contact with each other. Let's say we are bringing these two in contact with each other. So temperature T1 is greater. What does it mean? The molecules here would be oscillating at a higher amplitude here compared to the molecules here which are oscillating at a lower amplitude. Now, how the transfer of heat will happen? Now let's assume these two are brought with each other. This molecule might collide with the molecule of the second matter, and you know that according to the principles of collision, this transfers kinetic energy from body 1 to body 2. So obviously when the transfer of kinetic energy happens, this will after collision, the body 1 will have lesser kinetic energy compared to body 2. So what does it mean now? Now the temperature of T1 after the collision, it has gone down and T2 has increased up. So if you come to the macroscopic level, in other words, the T1 has transferred heat from it to the T2. I hope this concept is understood, right? So now let's move further. So this is the microscope at the microscopic level. Now exactly how exactly probably this heat is transferred in a regular life point of view, if at all we see that one, we can give one of the best analogy taken by any teacher probably in today's JEE classes or something like that. The different modes of transmission of heat. Let's assume that we there is a store where we have different suites. Different suites are there here, and we are supposed to or some weight or suite or whatever that may be, you are supposed to transfer it to another place, let's assume, and we have different people here standing. This is a classic example. I am saying everybody must have heard about this one. There are different people standing one in a line. So the conduction is what it exactly here, as I explained, you can see that there is a very subtle thing, a very important thing, that how do you understand after? I hope I explained that one, the collision point of view. With the collision point of view, no need. I mean, Mr. Win, I don't know that exactly what's your name. It need not be, probably until we are not talking till thermal equilibrium. Not exactly. Before that, I am saying. Attainment of thermal equilibrium is entirely different from what I am talking right now. These are the instantaneous points at which we are discussing the transfer of heat from one point to another point. I will come back to that one, all those things. Let us assume this some piece. This is to be transferred to place A to place B. If at all we have a connection, people lined up here, I will pass on the first packet to this guy, and next he will pass on to this one, he will pass on to the third guy, and he will pass on to, so it will reach the end, the B, in this fashion. This is what we call it as conduction, and notice that none of the guy he has shifted from his place. So this is very important. When we use medium in transferring heat from one point to another point, the medium doesn't, or the particles of the medium doesn't move from one point to another point, they will stay at their place. This is very critical. It just transfers, and exactly the same thing is happening with the collision concept. We can say that when a body it hits the other body, there need not be complete transfer of kinetic energy, or there may be complete transfer of kinetic energy depending on what type of collision it is undergoing. Mr. Win, I hope I am coming to your point now. Depending on what type of collision that it's going to encounter, we can say what portion of the kinetic energy is been transferred, whether it has completely transferred the kinetic energy, whether the complete momentum is transferred. So it's a bit of a discussion that needs to be taken along. We will just move ahead. I hope you people you can send across these questions, probably we will be able to answer that one. So this is the first one what I discussed is conduction mode. So in the material also, how the conduction happens? Conduction is happening because one particle transfers the energy to the other particle, and that transfers the energy to the third particle, and so on and so forth. So this is how from one point, one end, the energy it reaches to the other end. Now this is about the conduction. So what about the convection? Let's assume in the same shop, or in the between A and B two places, I will ask this guy who is standing here, probably he himself will come to this shop, he will take the packet and he returns back. So here the medium is moving from one point to another point. So this is very critical. Let's say this is convection. Let's assume we have a we have a candle which is where it's glowing and heat is going to come out here, and you put your hands or any vessel. So what exactly happens here is the air particle which are near to this candle, they themselves move. they themselves move, carry the heat from this point to the upper point. Of course, gravity plays a very important role here, very important role, remember. So, this candle, once it starts glowing, the air particles near this one, they gain energy and they expand, they lose density. Because of the loss in density, they move up. The next layer comes to the source of the heat there, it collects the energy, again it moves up, and the third layer comes down, it moves up. So, this is how the medium itself is circulating in such a way that the heat is taken by the medium and it transmits from one point to, I am saying transmits, it is not transfer, from, it is taking heat from one point to another point. So, this is about convection. So, we will come to this third one, the radiation part. Now, I have enough energy. Now, what I will do is that the entire packet, it is cut into smaller pieces in such a way that I throw these packets directly to tower B or the building B. So, this exactly happens in the case of radiation. Here observe, there is no medium or media involved in the case of radiation, because here independently I am throwing it out of my own ability. So, now the packet is moving without any medium. Here there is no transfer of medium or there is no movement of medium, there is no medium at all. So, this is how radiation is going to occur in the case of transmission of heat. Now, we will this is about probably the introduction that we can think of in the case of different modes of heat transmission. Now, let us go to the next important topic, the conduction of heat. This has got a very subtle, very important concepts here. Let me assume one source of heat energy which is at a temperature, let us say T1, and for our simplicity I assume another chamber or something which is at T2. For safer side, let us assume that this is at 0 degree or 0 Kelvin, let us say 0 degree Celsius. So, this is where the heat is supplied, and this is a rod which is transmitting heat from the point A to point B. Let us try to see how the transmission of heat happens, what are the mathematical equation that says, and what parameters on which the transmission of heat depends on in the mode of conduction of heat, right. If this is the case, now here let us try to enlarge this rod and look at the molecules. Probably these molecules which are set in the lattice, or let us say, since this is a metal, we are talking about the metals here, and that is very important. I just forgot to tell, in the case of conduction of heat, we need good conductors of heat, and we can also bring in the concept of conductors, insulators, and bad conductors and insulators. In this, the electrons, free electrons which are full of this rod, since in metal it is quite full, they receive the heat and they give it away to the next molecule which is, or the particle which is sitting next to it. So, slowly the energy or the heat energy it is going to receive the B here. Now, let us try to get into a little more detail. Let the length of this rod be L and the area of this rod, let it be, let us say, small a. Okay. Now, these two, the temperature difference T2 minus T1 or T1 minus T2, let this be delta T, this is the temperature difference. So what we say is that delta Q divided by delta T, we call this as heat current. We can see such kind of notations even in the current electricity, while only thing difference is that we use small q for standing for charge there and the same T there. This is proportional to, we can say, area. As we know that more the area, more number of particles will be involved. More the area, more particles will be involved. And if the temperature difference, if delta T is greater, more, if it is more, it is directly proportional to, no, heat transfer is going to be directly proportional to delta T. Now what is exactly the delta T it is telling about here? I will just come back to that one. It is inversely proportional to the length of the rod. We can say this delta T, or you can also write, I will come to the differential part there, this is something like the water falling from a particular height. Let us say this is the height, okay. The speed, the energy with which it is going to fall, if at all it is falling, so all the potential energy will get converted here, the complete energy. If you send this water on a little slopey side, the kinetic energy at the end it will be little lesser. If you go on reducing the slope, the speed with which the water is going to fall, it will reduce. In the same way here, the temperature difference, we can think this as the difference in height in the case of waterfall. So more the height, we can easily understand that it will have more the difference in height will fetch us better transmission of energy. So in the same way here also, the delta T, the better the difference in the temperature, the faster will be the transmission of heat. Now what next? You can say this part delta T, you can take it the other side, delta Q is proportional to A into delta T into, you can say, this delta T, this is the difference in time, divided by L. Don't confuse that one with this one. See, greater the amount of time that we wait, more amount of heat can also be supplied there. This is also another important issue. So now this is being the case, let us try to write this equation again. Delta Q by delta T is equal to, we write a constant of proportionality which is called as coefficient of thermal conductivity into delta T divided by L. This coefficient of thermal conductivity, this depends on the material property, the chemical property of the material. What does it mean? Probably whether it is a metal or non-metal, and whether it is good conductor, bad conductor. Good conductor, bad conductor and insulator are decided by this K. So for a good conductor, K will have a high value, and for a bad conductor, K will have a low value. So this high value for a good conductor and low value for a bad conductor. So looking at all these things, probably we will be able to decide how fast we need to send the current heat from one point to another point. All these things could be decided, right. Now let us move on to some of the other terminologies that we can think of understanding. Let's say, let's take a small differential element of this. Let's assume we had considered only the rod here. I will take here, so this is the T2 temperature and this is the T1 temperature here, the point A, this is the B, and I slice out a small portion of this one whose length is only dx, and this is a temperature, okay, I'll write this as here T1 and this is T2. I'll slice it out and write it here. The slab probably, yes, this is the thing. This phase has T2 temperature and this phase has got T1 temperature, right? Now this thickness is dx here. If at all, if I can write a differential equation for this one, I can write a small amount of heat Tq in a time dt that is supplied. This could be written as this K, don't write the small k here, capital K. So different notation stand different meaning in science. So area, instead of length, I write this as dt by dx, and remember we can include minus here, because here in taking the difference of dt, we always, this dt represents T2 minus T1. Remember, in the transmission of heat, T2 will always be lesser than T1 and it's a negative quantity. So this minus should be there, while in the case of the other one, in the previous, this here delta T, we could use it as we wish, because it was just a change. The change could be made according to our will and wish. So that is why when you talk about differential approach, so we need to include that minus sign. So this is about the equations of this thermal conductivity. We will go to the next important one, that's right. Oh, I just forgot to tell this one. This dt by dx, this is called as temperature gradient. So when it is d by dt, we call it as rate, and when it is d by dx, we call it as d by dx, in this case dt. So this is temperature gradient. If it is d by dt, in physics we tell it as rate, and if it is d by dx, we call this as gradient. Okay. Now another important aspect here is that the transmission of heat, how it's going to happen. Now a best example is that मान लो कि हमें किसी पाइप से हम पानी बाहर आ रहा, किसी पाइप से, assume that a pipe, यहाँ से पानी निकल रहा है जमीन पे, in different ways it's going to flow. The flow of water, you can relate it to flow of current, at the same time flow of heat also, remember this. In what way this is going to transmit? It flows on the floor. It doesn't flow if it is mud, it is not, doesn't flow immediately. When the point at which the water is falling, if it is dry, assuming that it is dry, certain portion gets absorbed, okay, certain portion, यहाँ पे छोटे छोटे, some portions they get scattered here also, okay, right. After this, the point at which the water is falling gets saturation, then from that point water flows. I hope you people must have experienced this one. The same way, what happens is that, let's take, let me erase this one. When the heat is transmitted, there are certain portion of the heat, it gets absorbed by the material, certain portion gets radiated into the environment, and certain rest is going to move. And what is that state is called as? Let's say we'll take the same two chambers. This is the rod here, and this is chamber A, this is chamber B, okay, and this is at a temperature say T1, this is T2. So we will say T1 is quite greater than T2, and the length of the rod is, we will say this is L. When the heat is given to this rod, this portion, let me change the color as well, this portion at which the first here the heat is given, this first absorbs it. It takes a little bit of heat, comes to a saturation. After that, a little heat will gets radiated into atmosphere. Then whatever that is left out, it's going to flow to the next point. And observe here, for the flow, whether it is water, whether it is heat or the current, there must be difference in what we call it as potential. In the case of electric field, it is electric potential. In the case of thermal, it is thermal potential difference. So, temperature difference, we literally call it as thermal potential difference. Now, the heat, it comes to the next point. Again, certain portion, depending on the specific heat capacity of that particular material, this gets absorbed, few part is going to get radiated and rest it's going to move again. This is how from one portion to another portion the heat is going to travel, and all these places, whatever the temperature that we take, say T dash, T double dash and T triple dash, so subsequent places the temperature will always will be lesser than the previous one. Assume if at all the temperature is completely same, uniform, you can be rest assured that heat is not going to flow. Just like water on a flat surface, it doesn't flow, it will stay there itself in the same way. Now, let us move on to the next one. These are all the explanations pertaining to this particular aspect. Now, after this third part, the state at which this heat is getting transferred, this is called as steady state. Why this is called as steady state? For any body to absorb heat, once it absorbs heat, the temperature of that particular portion is going to raise. So, let us assume that we are going to put, say, here some thermometers. Let us assume some thermometers are kept here at these points, and you can see that once these portions absorb heat, the temperature is going to increase there. So, you can be easily understanding this particular state. After a particular point, the body is not going to absorb the temperature. So, that is why this is called as a steady state. So, now moving on with this equation, I will just give you a small hint of giving you analogy. You can write this dq by dt is equal to, I am taking the magnitude, leaving out the negative sign, this K A in delta t divided by delta x, or L for that matter. Let us say this is L, I will write L here, this is L. Okay, I can see that this dq by dt, I can write it as ITH. I can call this as thermal current, which is equal to delta T. This is the temperature difference. We call it as thermal, potential divided by, you can write it as, just a minute, we will use the same notations also, delta V, let us call, and you can write this L by K times A. I write this as again ITH, this is thermal current into delta V, this is the potential difference, this is thermal potential difference, divided by thermal resistance. So, now the new point that I need to make here is that thermal resistance, this is proportional to L divided by inversely proportional to conductivity into area. This is what we see in Ohm's law also. Resistance, thermal resistance is equal to rho. This is the resistivity. We can call this as thermal resistivity, which is this thermal resistivity. This is equal to inversely proportional to thermal conductivity into length divided by area. So majority of the questions whatever that we now come across in the case of solving thermal conductivity problems, we can solve it easily with this kind of approach. Let's say I will take up two rods, say K1 and K2, which are connected in series. So you know that in the case of Newton's law, Ohm's law, resistance is going to add up. So the effective resistance, you can write it here. In this case, say it is R1 plus R2. You know that according to Ohm's law. So R1 I write it as, let's assume that lengths are same for both of the things for our purpose. Say L divided by A plus into K1 plus 1 L divided by K2 into A. So R effective, we can write it as here, say this is L by A, common take it outside, this is 1 by K1 plus 1 by K2. So you can write this as R effective, you can write it as L by K effective into A, which is equal to L by A, because it is same, area is same here there, 1 by K1 plus 1 by K2. So L by A cancels off. So the K effective, we can write it as, say K1 K2 divided by K1 plus K2. So this is your series connection. The next one I would like to take it up, say the parallel connection. Two slabs are connected like this, where you can say lengths are same, areas are same. Say this is the length L, and they are having K1 and K2, and from again Ohm's law, we can write the effective K here, we can write it as K1 plus K2 divided by, if both are same, we can write it as 2. These are the two things. Probably these are the factors that's going to make our calculations much easier. We will come to the previous contest question, that 540 grams of ice at 0 degrees Celsius and 540 grams of water at 80 degrees Celsius is mixed together. What will be the final temperature of the mix? This is calorimetry problem. Heat given is equal to heat taken. Mohan Chaitanya has given the right answer. So he is entitled for one atom session, which will be credited after this session. Okay. So now we'll go to today's contest time. You have only 60 seconds, guys. The question is, to manufacture utensils for cooking food, which type of the utensil is most suitable? The first one is high specific heat and low conductivity. Second one, high specific heat and low conductivity. Third one, low specific heat and low conductivity. And fourth one, low specific heat and high conductivity. So these are the things. Let's go to, after this one, we'll go to the growth of ice on lakes. We have got a lesser time. I'll just explain this concept. Probably we can wrap it up for today's session. Let's assume generally you can see that in the winter season, in the cold countries, the ice is going to pile up on water surface. Let's try to say we have already a slab of ice which is there, which is of length y on the water surface. After some time, it's going to grow to another value dy, and below this there is water. Okay. So assume that this temperature of the water at below this one is theta, and this is at 0 degrees Celsius. We know that ice is at 0 degrees Celsius, and you can write dq, and the heat is going to move through this one. So once the heat is lost, this upper surface of this water, it starts getting frozen. So dq, this you can write it as K, this is the thermal conductivity of probably water or ice, So this is area, let's assume some area there, and into 0 minus of, sorry, this is 0 here, this is 0 here, this is 0, and this is minus of minus theta, and as you know that this is the difference in between the two layers, and dt is the time at which it is going to grow, and the thickness, the length is, as we said, it is y, and if we since as dq1 at one particular surface, whatever the heat is lost should be the heat that is gained by the other surface. So according to this one, we can write from this dy by dt, we can write this as dy by dt is equal to k times theta rho, this is L into y, so by solving this one, probably you will get dt, if you solve for dt, it will be, this is rho L, try to think on these lines, rho L, what is that exactly, into y into dy. So by integrating you will get this as t, which is the time in which the ice is going to grow, the thickness, let's say if you can measure the thickness, the time it's going to grow is rho L divided by k theta into y square. So if at all we know two different thickness, t can be written as between, say, you can write this as y1 to y2. So this is rho L divided by k theta into y2 square minus y1 square. So this is the equation for the ice growth, and you can see that as the ice keeps growing, the loss of heat, it's going to be lesser and lesser, because ice is a very bad conductor of heat. So that's why after some time it's going to stop. So this square, sorry, here. So after this it's going to stop. So we have almost come to the end of this session. Today's whatever that we have learned, I have listed up here. The summary of today's class is that we have understood transmission of heat, different modes of transmission, how it's going to transmit in the case of conduction mode, what is steady state, which is very important concept, and law of thermal conductivity, that's the equation whatever that we wrote there, and the growth of ice on the lake surface. So thank you guys for joining me for today's session of this thermal conduction. Now it's time for CPP, and generally I keep since out of my experience I have picked up the best 10 different concepts. I don't say different problems which frequently occurs or all these things, 10 different concepts on probably which will give you help in understanding the concepts, and at the same time solve problems. Right away start solving that problem, and you have your own benefits solving at the first. So thanks a lot, have a nice time, good night.